The observations of Titan are taking place over a couple of different time periods, but basically stretching from early October to early November.
Right.
So we should get images in October, the first images from Webb of Titan.
Right.
We'll be very excited to look at those and see if there's dramatic changes since Cassini.
Welcome. AstroTalk UK is a not-for-profit podcast on astronomy, science and spaceflight. Launched in 2008, it's produced by me, Gurbir Singh, a writer based in the UK. I produce this podcast for my own education, but frankly, it allows me to meet fascinating people doing interesting things. It's primarily for my own education, and I share it as a free educational resource. No ads, no subscriptions, and you don't need to log in. For more, see the About page on astrotalkuk.org. Episode 103, Observing the Solar System with the James Webb Space Telescope. The JWST has already wowed astronomers and the general public with some incredibly spectacular deep space images. But did you know NASA has set aside a substantial number of hours for JWST to observe objects within the solar system? What's more, that program kicks in this autumn, so some images of planets and their moons, along with asteroids and comets, will be published before the end of this year. A team of astronomers, including planetary scientist Dr. Conor Nixon, will make use of the Guaranteed Time Observations, GTO, to observe the objects in the solar system from Mars and beyond. JWST cannot look back towards the Sun, so excludes the Earth, Venus or Mercury. The program is led by Dr. Heidi Hamel. In this interview, recorded in July during COSPA 2022 in Athens, Conor Nixon talks about the GTO and his role in observing Titan using the James Webb Space Telescope.
Conor Nixon, you work in NASA, and we're going to speak in a moment about the James Webb imaging Titan and other solar system objects, in addition to all the other fantastic work he's doing. But you work in NASA in the US, but that's not where you're originally from, is it?
That's right. I'm from the UK. I grew up in Northern Ireland, in Belfast, and I went to college in the UK and studied there for my master's degree and PhD. And at that time I got involved with NASA, so then I transitioned. But before that, yeah, I was in the UK for quite a long time.
And there's a Manchester connection you have as well.
That's right. So Manchester University is where I did my master's degree in radio astronomy, and I was there for a year, living at the observatory at Jodrell Bank in the beautiful Cheshire countryside.
Right.
And yes, I used the Lovell telescope, the Mark I telescope, for my master's degree.
So when did you move to NASA, and what is it, which aspect of space research and exploration are you working on right now?
That's right. So when I was doing my PhD at Oxford University, I got involved in the Cassini mission, and I helped to build one of the spectrometers that was a collaboration between several European countries and NASA. Oxford University had a responsibility for just a small piece of the instrument, and I got to travel back and forth and meet lots of people at NASA. So then when I graduated, I really wanted to continue on the Cassini mission. So that's what I did. I went and joined the mission when it was soon after launch.
Right.
I stayed there right to the end.
And were you working on the spectrometer aspect of Cassini?
That's right. It's called the Composite Infrared Spectrometer, CIRS, and that's the instrument that I worked on for several decades, and all the way through from before launch to after it dissolved into Saturn's atmosphere.
So I'm sure a lot of the experiences you built up during that time, during the Cassini mission, will inform what you're going to be doing with James Webb. So just take us through about the exploration of the Saturn system, which prior to the main topic I want to talk about, James Webb looking at Titan, what do we know about Titan and which spacecraft and instruments have been used to provide that information?
So the first spacecraft to really get close to Titan was the Voyager 1 spacecraft, which flew by in 1980, and that was the first time that we were able to get a radio signal to pass through the atmosphere from behind, and actually told us where the solid surface was. Until that point, we actually didn't even know where the solid surface was, because all we could see was the top of the atmosphere. So there was actually an ambiguity about how big Titan was. That lasted until 1980. And so the Voyager 1 spacecraft was diverted to make a close flyby of Titan, while the Voyager 2 spacecraft went a different direction and went on to Uranus and then Neptune. So following that, there were missions sent to the Jupiter system, which was Galileo, and then to the Saturn system, which was Cassini-Huygens, I should say, which was basically two spacecraft. There was an orbiter, which was a Saturn orbiter, built by NASA, and then there was a European part, which was the Huygens probe, named after Christian Huygens, the discoverer of Titan in 1655, a famous Dutch astronomer and polymath who did many things. That probe was sent to land on Titan's surface, and that was the most distant landing, and remains to this point the most distant landing ever accomplished by humanity.
And just going back to the Voyager mission, I wasn't aware that that was the first time that the dimension, the size of Saturn was known for the first time, because of the radio transmissions from the other side. So in addition to giving you the information about the size, the physical size of Saturn, did that radio transmission through the atmosphere of Saturn give you any more indication about the nature of the atmosphere of Saturn?
It did, exactly. So we do what's called a radio occultation measurement, and there's actually a refraction that goes on. So if you've ever placed a stick in a swimming pool or a lake, you see it kind of bends. It appears to bend at the surface, and that's refraction. So what happens is that when the radio signal, so when the spacecraft goes behind the planet, as it gradually goes behind the planet, the radio signal goes from traveling straight through space to traveling through the atmosphere, and at that point it begins to bend. And the amount of bending can be measured, so we know exactly where and how fast the spacecraft is traveling, so we know its trajectory. But then when the light ray begins to bend, or the radio signal in this case, that amount of bending gives us the density of the atmosphere. And then from then we can work out other things like the temperature as well.
Right. I take it was not sophisticated enough to give you any indication of the chemical constituents of the atmosphere.
So we have to get to the temperature profile, we have to make assumptions about the composition. The radio signal didn't give us that, but other instruments on Voyager did give us information about the composition. So there was significant uncertainty still at that point about what the atmosphere was actually made of. It was thought that it could be mostly nitrogen, N2, for reasons that, simple reasons like it doesn't condense at cold temperatures. But it wasn't known for sure. But then the ultraviolet instrument on Voyager was actually able to measure ultraviolet emissions from the N2, and that actually told us what the atmosphere was made of, which is mostly N2. About 95 to 98% of the atmosphere is N2, and then most of the remainder is actually methane. And that had been known much earlier, from 1944, from another Dutch astronomer. The Dutch have a lot to do with Titan, called Gerard Kuiper.
Oh yeah.
Who during the war went to McDonald Observatory in Texas and observed absorption lines of methane, and that was the first clue that Titan actually had an atmosphere.
And Kuiper belt is the object named after him, I'm guessing, same Kuiper. So Voyager, as you say, gave us the first. I mean, I remember the images in those days. You were far too young, I'm sure, if you were around there, and they were just spectacular. And it's actually that aspect that gave me and many, I'm sure, of my generation an interest in astronomy and space, which has never left us. So Voyager was a terrific success. Cassini-Huygens, as you say, two spacecraft. The Huygens was a lander, and Cassini was another tremendously successful mission. What did both Cassini from orbit and the lander on Titan, what did we learn from those two probes that perhaps informed the kind of observations that would be conducted by James Webb?
Yeah, absolutely. So there were several really big notable discoveries about Titan. Probably the most impressive was the discovery that it has lakes and seas of hydrocarbons on its surface, actually on the North Pole, and interestingly, only on the North Pole, and not in the lower latitudes or on the South Pole, but only in the North Pole. And those lakes and seas are not water because it's too cold for water to exist as a liquid. Water, in fact, forms the crust, the actual bedrock, or as we call the regolith of Titan. Right. So the surface, if you were walking around on the surface, you'd be walking around on mostly water ice, frozen as hard as rock. But then there's pools of hydrocarbons, which are basically petroleum, or LNG, liquefied natural gas, methane, ethane, propane, which is what you have in those tanks used for your barbecue grill. So that's what's on the surface, actually forming the lakes and seas. So that was a big discovery from Cassini, from the radar instrument and the imaging. One of the other very interesting but a little bit less well-known discoveries was that there are dunes on the surface of Titan.
Like sand dunes.
Like sand dunes, except they're not made of the same material. Again, so Titan, being an exotic place, does not have that silicate material which makes the sand on the Earth, which is kind of ground up rock. So, in fact, the dunes are made of sort of a plasticky material, which is not very well known. But it appears that this stuff comes out of the atmosphere. It's kind of like a smog. And these particles kind of coagulate, and then it's dry enough on the surface that they can basically just blow around and form dunes of sort of smog, or you can think of it as soot almost.
So there is some sort of a weather cycle. Well, it's like we have here with rain. On Titan there is winds, dunes, and I'm guessing it's the hydrocarbons that form the cycle?
Exactly. So on Earth we talk about hydrological cycle, which is the cycle of water evaporating, forming clouds, and then raining down and carving river channels or maybe glaciers, and then eventually making its way back into the ocean. So on Titan it does have its own hydrological cycle, or sometimes we call it a methanological cycle, because the substance which is able to be in both a gaseous state and a liquid state close to the surface is methane. So it turns out that the surface temperature of Titan is very close to the evaporation temperature of methane, which means you just need a tiny bit of sunlight to begin to evaporate the methane, and then it forms clouds, and then it actually rains out on the surface, and we can see that there are channels carved, maybe a bit like we see even on Mars or certainly on the Earth, but the channels are being carved by methane.
Flowing like a river.
Methane rainfall, and they carve channels, and then they form these lakes and seas, and we think perhaps in the past there may be more widespread even oceans of methane that are now dried up, and basically where the Huygens probe landed was actually on the bed of an ancient methane ocean. Really exotic stuff.
Yeah, and just going back to the pools of liquid hydrocarbons near the North Pole, first of all, I'm guessing there aren't any other bodies within the solar system with any form of liquid on the surface. And why is there any understanding about why they only exist in the North Pole of Titan?
That's right. So other than the Earth, Titan is the only place where you can go to float a boat, or put a submarine, at least on the surface. And go sailing or windsurfing or something like that. But it's a good question. Why the lakes and seas only on the North Pole and not anywhere else? So it looks like on the South Pole we see dried up seas, and there's one lake it's actually called Lake Ontario or Ontario Lacus on the South Pole, which appears to be in the process of drying up. So even during the course of the mission, it appeared to kind of shrink its boundaries, and we think that it's probably a bit sort of viscous, which is why I didn't include it when I said that all the seas were on the North Pole. There is one that's been seen on the South Pole, but it's probably a bit sort of sludgy or viscous, and appears to be in the process of drying up. So maybe it's more analogous to like a swampy type thing. Again, hydrocarbons, but we think this one is mostly ethane, which is a slightly heavier substance than methane. Now the reason for the lakes and seas being on the North Pole and not the South Pole is thought to be due to very long cycles in the wobble of Titan's polar axis, which basically means that for certain thousands of years it gets more sunlight at one pole than the other. So that basically allows the liquids to migrate. When I say migrate, they're not crawling across the surface, they're evaporating and then raining out preferentially on the north and getting evaporated a little bit less on the north, so they basically all migrate. But maybe some thousands of years in the future, they would actually re-evaporate and migrate back to the south, but not on an annual time scale, but on many thousands of years.
Right, and we know that there is a mission going within the next couple of years, but won't be until the next decade until it arrives, Dragonfly, that will actually, it's going to be a quadcopter type mission.
That's right.
And that will be able to, certainly be able to examine the surface and the atmosphere. Will it be going anywhere near these lakes, do you know?
Actually, no. So you're right, the Dragonfly mission, which is a sort of like a very big drone. It's sometimes called a quadcopter. It's really an octocopter. It has 2 rotors at each corner, and it's sort of lifting a large sort of relocatable lander, basically something about the same size as one of the big Mars rovers like Curiosity or Perseverance, basically lifting it up and moving it a few miles at a time. And it's been targeted to go to the equatorial parts of Titan, and basically it's going to land amongst these dunes, these hydrocarbon dune fields, and it's going to sort of sit down in the space between 2 dunes, and then it's going to sort of hop over these dunes. And one of the goals is to get to a large crater, which is called Selk. I think it's around 80 kilometers or so in size. And one of the reasons is because the crater actually allows some excavation through the crust to a deeper level. So you begin to see a little bit of sort of what's below the surface. And so that's where the mission is sent. Part of that is also due to the fact that when you get to the poles, communication can be a little bit more difficult depending on which season you're in. Obviously there's a winter season at the poles where basically you're out of sight from the Earth. So the equatorial regions are good for communication.
And it won't be accompanied by an orbiter, so it will be transmitting to Earth from the surface of Titan.
Direct to Earth from the surface, that's right.
And it's quite a thick atmosphere. I'm sure that will help with flight compared to what amazing but difficult job Ingenuity has on the surface of Mars. That's going to be a challenge for communication, because you've got all this haze between the quadcopter and Dragonfly and Earth. I'm sure all the maths has been done, but it's quite a challenge transmitting from the surface of a planet which is quite heavily veiled with something or other most of the time.
Yeah, so fortunately the atmosphere is relatively transparent to radio waves. The same is not true at shorter wavelengths with with visible light and infrared and so on. Once you get to long enough wavelengths, the atmosphere is pretty transparent. the particles that are in the atmosphere are very small, so they don't tend to scatter those long wavelengths as much as they scatter short wavelengths. So there's a property of scattering, which means that once the wavelength gets similar to the size of the particle, you get a lot of scattering. But when you get to much longer wavelengths, it's sort of transparent. There is an issue with power, getting a signal all the way back to the Earth. Takes a lot of power, and you've got to make sure you point in the right place. So there's a cone that you want to aim towards, and the signal is going to be pretty weak, and it's going to trickle back, not very quickly. But given that the mission is nuclear powered, it's going to last some years, so we'll get a lot of information back.
Well, that sounds really exciting. So Cassini lasted for almost 2 decades, but the lander, Huygens, is very short, so you have some understanding of the environment in which Dragonfly will operate. And I'm guessing in just the same way that Voyager informed Cassini, Cassini will inform the kind of observations we'll conduct from James Webb. So first of all, it is quite remarkable, and I hadn't appreciated early on, that James Webb will be looking at objects within our solar system. So I understand that's something that was in the design from the outset.
That's right. So there's a program called GTO, Guaranteed Time Observations, specifically for the solar system. There's other similar programs for astrophysics and exoplanets and so on, but there is a guaranteed time program within the solar system where around 100 hours, a little over 100 hours, are set aside in the first cycle, JWST cycle 1, to look at all the objects in the solar system that are further away from the sun than JWST, because it cannot look closer to the sun, because that would mean turning its sunshade in such a way that it gets sun on its radiator, and that's not allowed. It's an infrared telescope, and it has to stay cold. So it can point at Mars or anything beyond Mars. So that includes the giant planets, the satellites of the giant planets, the Kuiper belt, and many asteroids, and even some asteroids that will cross the orbit of the Earth, as long as we see them when they're beyond the orbit of the Earth. So they're called NEOs, near-Earth asteroids. So all those will be studied by JWST. In fact, as I understand it, right now there's some further commissioning underway, which is basically to check that the telescope can turn fast enough to track some of the faster asteroids. So its speed has been validated up to a certain amount, and they're now trying to push that a little bit further to see slightly faster asteroids. But Titan is one of those objects that JWST will be looking at in its first year, and I have the good fortune to be the lead or the delegated deputy for the Webb solar system observations, specifically of Titan.
So I've seen these terrific spectra of exoplanets released just last week of the atmospheres of exoplanets taken by the James Webb. I'm guessing that's one of the things that you'll be asking that James Webb observations will look at, the atmosphere of Titan from its L2 point.
Absolutely. So one of the reasons why we're so fascinated by Titan is that it's the only moon in the solar system that has a substantial atmosphere. There's a couple of other very tenuous atmospheres, but Titan really has a dense atmosphere. And in that sense, it's much more like one of the terrestrial planets, like Mars or Venus. But at the same time, its atmospheric composition is radically different than Mars or Venus. So those planets and also the Earth have an oxidizing atmosphere with oxygen, CO2, those sort of substances. But there's a lack of oxygen in the atmosphere of Titan, and that means that substances such as methane can react in what we call organic chemistry, which basically can form very large, complex substances, which could be of great interest for perhaps forming precursor chemicals that could have been used to form life back at the start of the solar system. So Titan's like a unique natural experiment underway that that we can look at. As I said, the only moon with an atmosphere, and with the Webb telescope, it's perfect for the job of actually looking at the chemistry of the atmosphere. So it turns out that molecules have vibrations. Once you get two or more atoms and form a molecule, the molecule can interact with radiation by vibrating, and these can form different modes like stretching modes or scissoring modes, and all those actually appear in the infrared part of the spectrum.
So some exciting, you mentioned chemistry, but there's a lot of organics out there, and I guess this is the exciting bit. You're not quite sure what you'll find when you start looking. So you've got some time on James Webb to look at Titan. What sort of schedule and what we'll be looking at, and when do you think you'll be publishing some results?
Yes, there's going to be a lot of interest and even a little bit of pressure to get results out quickly. So one of the issues about the guaranteed time observation is that normally when you apply for time competitively on a telescope, you get what's called a proprietary period. That means that the PI, the principal investigator of the data, gets typically a year to look at the data before it goes on general release. Now, in this particular circumstance, the bargain that was made to get this set-aside program was that it would be sort of like community service. So basically, the data would be given without competition to a bunch of scientists, including myself, to design the observations. But then we don't own it.
Right.
So it becomes public immediately. There's no proprietary period. So in effect, we could be in a little bit of a race, to look at the data before everyone else in the world gets their chance to weigh in. Although I would say that we, at least the Titan group that I'm leading, which is about a dozen people, are really the experts in looking at this type of data. So I think we'll be able to do a pretty good job pretty quickly.
So usually the principal investigator and the team he or she leads get this time period when they can look at the data and publish papers. In this instance, there's no time period allocated to them, go straight out to the public. I suppose, I'm sure some individuals will be disappointed, especially those who put the time and effort in building the instruments for them. But I'm guessing that as a consequence, there'll be many more papers released, perhaps sooner or earlier than otherwise would have been the case.
That's right. So there's a trend now towards having this open access to data, so that, for example, the ALMA telescope observatory, which I've used quite a bit in Chile, which is an array or a network of radio antennas. The data is proprietary. It's exclusive to the PI for 1 year, and then after that point, it goes in a data archive online, which is searchable, free. Anyone in the world can go on their website, download ALMA data, and begin to do science with it. And the idea is that it will increase the amount of science papers, as you mentioned, that come from these very expensive facilities by basically allowing use and then reuse and reuse and reuse of the data as other people do it. Whereas in the past, observatories tended to be private, and then they tended to just hold on to their data and not make it public, and you'd have to put in a special request. So the idea is that you basically get more bang for your buck, right? You get more science papers for the expenditure that goes into acquiring the data.
Yeah, that's a compromise, and a fair compromise, I guess. So, in terms of schedule, when do you think you will have that first access to James Webb to look at Titan, and roughly when will we see the results publicly?
Yeah, it's very exciting. The data's coming quite soon in October.
Right.
The observations of Titan are taking place over a couple of different time periods, but basically stretching from early October to early November.
Right.
So we should get images in October, the first images from Webb of Titan.
Right.
We'll be very excited to look at those and see if there's dramatic changes since Cassini. We'll be looking at the haze. We'll be looking through the haze to the surface at some wavelengths. and we'll be looking for clouds and meteorology and seeing if there's any. We know that there's methane storms, for example, on Titan. Cassini caught just one big storm, so it saw a storm front sweeping across Titan that was huge, I think 1,500 kilometers long, and it was sort of sweeping across like a storm front, and appeared to darken the surface with methane rainfall, which then later re-evaporated, and the surface went back to its original color. So we'll be looking for that type of event if we're lucky, but we'll definitely be looking at the surface. And one of the things that Webb will do with its spectroscopy is telling us more about the composition of the surface.
Now I'm sure the Cassini had a much smaller aperture instrument compared to James Webb, but James Webb's much further away.
That's right.
The resolution provided by James Webb won't be anywhere near what Cassini provided, I take it.
That's right, you're right. It's a much bigger telescope, but it's much further away. Here we're close to 9 or 10 astronomical units from Saturn, which is an astronomical unit being the distance from the Earth to the Sun. So close to 1 billion miles of that order. So it's pretty far. And even with Webb, we'll be a little bit limited. So we're expecting at the very best, which is at the shortest wavelengths, we'll get about 30 pixels across, which means we'll get something that's about 30 by 30 in our image, so sort of 900 sort of pixels, that sort of level. As we go to longer wavelengths, there's an effect which means that the pixels get bigger. So we'll get to at the middle part of the infrared, we'll get sort of 10 by 10 grid on Titan, and it's not going to be as sharp as obviously as Cassini, but one of the good things about Webb is that it will give us many more wavelengths that we didn't see before.
And I'm sure, looking at the spectra of the exoplanet, the spectroscopy element of James Webb, looking at Titan is going to be quite spectacular, even though it's so far away. Just one final thing. We've been speaking about Titan, but what's the program for James Webb looking at other bodies within the solar system? Is there a schedule that you're aware of already?
That's right. So this solar system guaranteed time program, which is led by a great scientist called Heidi Hammel in the United States, is a sort of umbrella program which has about a dozen different components in it, including Mars observations, Titan, which is the one that I'm involved with, giant planets, led by Lee Fletcher, who's at Leicester University in the United Kingdom, and asteroids, comets, and other objects. We'll be searching for plumes on Europa, and all sorts of exciting stuff. So all this solar system science is being spread out over the first year. So approximately from this summer to next summer, maybe a little bit over a year. And you'll see those pictures coming out, pictures of Jupiter, Saturn, Uranus and Neptune, which will be very exciting because they've not been visited by a spacecraft in a very long time. Uranus in 1986 and Neptune in 1989 by Voyager 2, and nothing since then. So the Webb pictures will be really amongst some of the best images that we've had since that time.
And when that happens, maybe even later this year, I'd like to catch up with you again once that information is available.
Absolutely.
For the time being, Dr. Conor Nixon, thank you very much indeed.
Thank you, Gurbir. It's been a real pleasure talking to you.